Welcome to Lecture 31, First Order Differential Equation Examples in Physics. Examples from Physics, First Order Differential Equations. So in today's lecture we're going to talk about three different examples. The first one is going to be air resistance. Air resistance can take a number of different forms. We're going to first analyze what happens when the air resistance is linear in the velocity. But before we even start that, we want to look at the case with no air resistance. So we're going to assume a mass m is dropped from a height h and falls due to gravity. Newton says, and I'm going to take the positive direction as being down, that the mass times dv dt, that's the acceleration, is equal to mg, which is the force. It's positive mg because the positive direction is downward. The m's are going to cancel from both sides, and I'm going to get dv of t dt is equal to g. And that's the differential equation I need to solve. Well, this is a nice, simple, separable equation, so it's easy to integrate it. Integral from 0 to v dv prime equals integral from 0 to t g dt. I get v minus 0 equals gt minus g times 0, or v is equal to gt. Okay, really simple. You learned this in probably the first week of the freshman physics class. Now, let's assume the air resistance is proportional to the absolute value of the velocity. If it's proportional to the velocity, we need it always to be opposed to the velocity. So it's going to be minus k times the absolute value of v. Now, in this particular case, with the motion going downwards and the positive direction being downwards, v is always positive. So the absolute value I can get rid of, and the force will always be just minus kv. And so Newton says m dv dt is equal to mg minus kv, which is our new force that we're adding on due to the air resistance. I can divide by an m, and I get dv dt equals minus k over mv plus g. Or I can bring the k over mv to the left-hand side and get dv dt plus k over mv is equal to g. This is the standard form for our linear first-order differential equation with q equal to k over m and r equal to g. So now we just plug into our cookbook. We start with q equals k over m. We integrate that. We get kt over m. And then we plug into the equation where we integrate r times the exponential of the integral of q. We can work out that integral as well. We get gm over k exponential of kt over m minus 1. And then we can form the full solution. Now, because v at t equals 0 is equal to 0, we don't actually have the homogeneous term in our solution, and we just get the particular solution. So we get v of t is e to the minus kt over m times gm over k e to the kt over m minus 1. I can bring that exponential into the square brackets and get gm over k is 1 minus the exponential of minus kt over m. So let's take a look at this equation. Now, if t is equal to 0, I get v of 0 is equal to 0. That's our initial starting condition. But if I look at for small t, I can expand that exponential as 1 minus kt over m. And then I have 1 minus the quantity 1 minus kt over m. That just equals kt over m. The k over m cancels the m over k out front, and I just get g times t. Well, that's actually what that's what we got for the velocity dependence on time in the case where there was no air resistance. So if we start off the system with a velocity equal to 0, the initial air resistance is 0, and so we recover that solution for short times of what we got when there was no air resistance. But now, of course, if we let t get very large, what we're going to find is there's a terminal velocity. The velocity is going to approach gm over k, and so we see there's a terminal velocity. We can't get any faster than that, and the value of the terminal velocity is just given by gm over k. Okay, so now we're going to look at the case where the air resistance is quadratic in the velocity, and in this case the force is just going to be some new constant, minus k prime times v squared. And then what Newton says is the mass times the acceleration, m dv dt, is equal to mg minus this k prime times v squared. And I'm going to divide both sides by m. I get a dv by dt is equal to minus k prime over m v squared plus g. This is a separable equation. I'm going to divide by the right-hand side and multiply by a dt. I get dv over g minus k prime over m v squared equals dt. I can actually integrate both sides. Let's see how that works. So I'm going to first factor out an m over k prime. I'm going to write this as an integral from 0 to v dv gm over k prime minus v squared. Now I'm going to expand that in a partial fractions, I still have my m over k prime term, the integral 0 to v dv, and then I can write it as 1 over the square root of gm over k prime minus v plus 1 over the square root of gm over k prime plus v. But in doing so, I generate a term in the numerator that is 2 times that square root. So I have to multiply by 1/2 times the reciprocal of that square root, which is k prime over gm. Please check very carefully that you get the same result if you work this out. Then, of course, the left-hand side is trivial. It's just the integral from 0 to t dt prime, and that, of course, just equals t. So now the integral of each of these terms that I expanded in partial fractions is just a logarithm, and because I have a minus v in one of the terms and a plus v in the other one, I'm going to get the ratio of those two terms in the logarithm. And what we find is 1/2 the square root of m over gk prime. That's what we get when we look at all the constants that are left. The logarithm of the square root of gm over k prime plus v divided by the square root of gm over k prime minus v. That whole thing is equal to t. Now what I'm going to do is I'm going to divide by the constant on both sides. So I'm going to multiply by 2 square root of gk prime over m, and then I'm going to take the exponential. So I'll get e to the 2 square root of gk prime over m times t is equal to this ratio, square root of gm over k prime plus v divided by square root of gm over k prime minus v. Now what I'm going to do is I'm going to solve for the v. Now, you need to actually sit down and do this. What you're going to find is you're going to get in the numerator something that goes like 1 minus e to the 2 times that square root, and then the denominator you'll get 1 plus e to the 2 times that square root. And then what we do is we multiply and divide the numerator by e to the minus square root times t. And then you can recognize that the numerator is going to be 2 times the hyperbolic sinh, and the denominator is going to be 2 times the hyperbolic cosine. And of course, hyperbolic sine over hyperbolic cosine is just equal to the hyperbolic tangent. And when all the dust settles, you find v is equal to the square root of gm over k prime times the hyperbolic tangent of gk prime over m. Now let's take a look at this for small t once again. For small t, the tangent goes like gk prime over m times t. And when I plug that in, I find I'm going to get v goes like gt, just like we had before. But this again will have a terminal velocity because for large argument, tangent approaches plus 1. So the terminal velocity will be the square root of gm over k prime. It's a different terminal velocity because we have a different kind of a force acting on the system. It goes like v squared instead of v. Okay? You also can check to see that this satisfies the differential equation. V at t equals 0 is equal to 0. And then if you work out the derivatives, you find it actually does satisfy that differential equation. And as we said before, we get this new terminal velocity that's different than the one that we had the last time. All right, that's all I want to talk about with regards to air resistance. We have 2 more applications we're going to look at. The first one is Newton's law of cooling. This is something that is not often taught in physics courses, but it's really a pretty easy concept. What Newton said, let's start off with some definitions. T of t is the temperature of the object, and T0 is the ambient temperature around us. Then Newton's law of cooling says that the derivative of the temperature of the object with respect to time is equal to minus k times the difference in temperature of the object versus the ambient room. That's a pretty easy to understand equation. There's some constant k that we have to figure out what it is for any given example if we want to apply Newton's law of cooling. But it's a pretty straightforward equation. It simply says that if there's a temperature difference, that temperature difference is going to decay proportional to what that temperature difference is. So if I have a large temperature difference, the cooling is much faster than if I have a small temperature difference. All right, this is a nice linear first order differential equation. We're going to assume that the object starts at a temperature T1 at a time t equals 0, and we want to solve for the temperature profile T of t. Q of t in this case is equal to k, and R of t is equal to k times t0. So let's work out the integral from 0 to t dt prime q of t prime. That's just kt. Then the integral from 0 to t dt prime of kt0 times the exponential of kt prime. This is essentially the integral we worked out on the first page. It's equal to t0 times e to the kt minus 1. And what we find is t of t. Now I have a non-zero initial value, so I'm going to have that homogeneous equation as my first term, t1 e to the minus kt, plus t0 times 1 minus e to the minus kt. Now, once again, if you look carefully at this in the limit as t equals 0, you see that the initial temperature is equal to T1. And then, of course, we let t go to infinity, we're going to find the final temperature is equal to T0. That's all what we expect it to be. But let's check as well that it satisfies the differential equation. So let's take the derivative with respect to t. I get minus kt1 e to the minus kt plus kt0 e to the minus kt. Now I can factor a minus k out of that, and if you look at what t of t is in the line above, you see I can write that as minus k times t minus t0. That's all that there is to it. And that indeed was the original differential equation. So we verified that this is the solution to this differential equation. All right, we're going to have a demonstration of this, and you're going to have an opportunity to work through some numbers that work explicitly for Newton's laws of cooling in the in-class exercises that we're going to do that are accompanying this lecture. All right, we have one more example we want to talk about. We're going to talk about rockets. Now, Newton's second law, you've been told this, but sometimes it's hard to remember, is actually about the rate of change of momentum. It's not mass times acceleration, it's the rate of change of momentum. Now, in a rocket, there is acceleration, of course, but there's also a change in the mass. So the derivative of the momentum with respect to time is m dv dt, that's just mass times acceleration, plus dm dt times v, that's the change in mass times the velocity. And that whole thing will equal the force that's being applied on the system. Now, for our rocket, we're going to assume it has an initial mass m0 and an initial velocity v0. It's going to expel fuel at a constant rate beta, such that dm dt is equal to minus beta. Now I can integrate that and find m of t is just equal to m0 minus beta t. And the fuel is expelled with a fixed exhaust velocity v exhaust. Finally, we're going to assume the rocket feels a constant gravitational force equal to minus m of t times g. Then we can put this all together into Newton's equation. We're going to get the mass as a function of time, m0 minus beta t times dv dt, minus, so dm dt is minus beta, and notice here we're multiplying by v exhaust, not v. This is a subtle point about rockets and about the rocket equation, but when you go through a balance of momentum, you have to take into account how fast the fuel itself is burning, because that's the momentum that is leaving the rocket, and that's the momentum kick that the rocket gets due to the fact that the fuel is being expelled out of one end. So it ends up being minus beta times v exhaust, not v itself. You can sort of easily convince yourself that this is the case. When I initially start, when the velocity is equal to 0, I of course will be having some effect due to the burning of the fuel, and if I put a v instead of v exhaust, I wouldn't get that effect. Okay, then it's equal to minus the mass times g. The mass is just m0 minus beta t, and we multiply that by g. All right, now we have some rearranging to do. First, we're going to divide by that m0 minus beta t, and we're going to find dv by dt is equal to minus g plus beta v exhaust divided by m0 minus beta t. This is once again a separable differential equation. I multiply by a dt, I integrate both sides. So when we integrate the first side, it's just an integral from 0 to v, or v0 to v of dv. That just equals v minus v0. And then the right-hand side is an integral from 0 to t dt prime of minus g plus beta v exhaust over m0 minus beta t prime. Both terms are trivial to integrate. The first one gives minus gt. The second one gives v exhaust times the logarithm of m0 over m0 minus beta t. And so both terms are easy to work out. Now we're going to have to massage these equations a little bit more. We want to get v of t, and so we bring the v0 over to the right-hand side. We get v of t is equal to v0 minus gt plus v exhaust, logarithm of m0 over m0 minus beta t. Let's check to make sure that that works. If we substitute in t equals 0, that logarithm term is the log of 1, which is 0, and so I just get v0 minus 0, or I just get v0, which is what it's supposed to be. If I take the derivative with respect to time, I'll get a minus g, and then I'll get a minus v exchange times 1 over m0 minus beta t times minus beta. And that, of course, equals minus g plus beta v exhaust over m0 minus beta t. So indeed we have found the solution. Now, as I'm running this rocket, at some point in time the fuel's going to run out and the denominator will become a constant. If we can increase either beta or the exhaust, we're going to increase what that final velocity is at the time that the fuel runs out. You can convince yourself just by looking at the v of t equation that the bigger the v exhaust is, that's the obvious one, but it turns out also the bigger the beta is, the larger that final velocity is going to end up being. All right, that's all that we have time for today with these 3 examples. In class, we're going to be going through explicit examples where we're actually plugging in some numbers and analyzing a couple of situations related to these different problems.